In this video, we're going to introduce the fields of an Ethernet frame. Remember, Ethernet is for network interface card to network interface card on the same network. And to mention, you see these numbers underneath here. These are the number of bytes for each one of these fields. If you want to then translate this into bits, just multiply each one of these numbers by 8, and it will give you the number of bits. So the first field is the preamble. This is used to just get the NIC card, the receiving NIC, in sync with the bits that are coming down the cable. The start frame delimiter, this indicates to the receiving network interface card that following this start frame delimiter will be the actual information associated with the Ethernet frame. Next, we have the destination MAC address. The destination MAC address is the MAC address of the destination on that network. So that's the MAC address of the NIC card where this Ethernet frame is going to on this network. The source MAC address, this is the MAC address of the device that originated this Ethernet frame. The MAC address of the network interface card, the Ethernet NIC, that originated this Ethernet frame. Next, we have the length or type field. So this field here can be one of two things. It might be the length, and that would be the length of the data, what we sometimes call payload, how many bytes are in the data portion of this Ethernet frame. Or it might be a type field that says, what kind of data is this? Is this an IPv4 packet? Is this an IPv6 packet? Next is the actual encapsulated data. So this might be an IPv4 packet, could be an IPv6 packet. And then along with the IPv4 packet, let's say, could be other protocols as well. So this is all the data. This could be the IPv4 packet with the TCP header along with the HTTP header, or whatever information has been encapsulated. And actually, Ethernet doesn't care what kind of data is it. It's just delivering this data from network interface card to network interface card. Last, we have what's known as the FCS, frame check sequence. This is used by the receiving device to do some error checking, to make sure there were no errors along the way in transmission. In this video, we're going to look at two different types of addresses: physical, or the MAC addresses, and logical, or the IPv4 addresses. So here we have host H3, and we can see that it has the IPv4 address 192.168.200.3. The network portion of the address is 192.168.200. The host portion is .3. The subnet mask is what defines or determines the network portion from the host portion. So as you can see, actually, in this network here, where this cloud is, all of the addresses begin with 192.168.200. And then they have different host portions of the address. .3 for H3, .4 for H4, etc. In this network over here is the 192.168.1.0 network. So you'll notice that all of these devices have an IPv4 address that begins with 192.168.1. something. So I click on the plus sign here by H8, host 8, and it shows the network address 192.168.1, and the host portion of the address is .4. Okay. So what we're going to do is, if we send a packet from H3 to H8, it uses the IPv4 addresses to do this. The source IP address of the packet would be the source IPv4 address of H3, 192.168.200.3. The destination IPv4 address of the packet would be that of host H8, 192.168.1.4. Those addresses never change. So the source IPv4 address and destination IPv4 address of the packet remains the same as it traverses from one network to another and across as many networks as it takes to get there, to get to the destination H8. Previously, we talked about physical addresses, the Ethernet MAC address. Although not shown here in the animation, let me just explain that the destination MAC address is used to deliver the packet, the encapsulated packet, in an Ethernet frame from H3 to the router. So the Ethernet frame carrying this IPv4 packet would have a source MAC address associated with the Ethernet NIC card of H3. The destination MAC address would be that of the router's Ethernet interface that is attached to the 192.168.200 network. So the source MAC address is that of H3. The destination MAC address would be that of the router's interface on that network. Once the packet is delivered in the Ethernet frame to this router, the router will remove the Ethernet frame. It will then look at the destination IPv4 address of the packet, look it up in something called its routing table, and forward that packet out towards this other network, the 192.168.1.0 network. It will be encapsulated in a new Ethernet frame. The source MAC address will be that of the router's Ethernet interface connected to the 192.168.1.0 network, and the destination MAC address will be that address of the NIC card of host AH. So the key point here is the IP addresses, the source IPv4 address and the destination IPv4 address in the packet remains constant, remains the same as the packet goes from the source to the final destination. The Ethernet MAC addresses, the physical addresses, they will change as they go from one network to another network. The Ethernet MAC addresses, the physical addresses, are what we say are for NIC card, network interface card to network interface card communications on the same network. As that packet goes to a different network, is forwarded to another network, then new MAC addresses, new physical addresses are used for the NIC card to NIC card communications on that network. So for a network professional, it's important to understand the differences between how a logical address is used for end-to-end delivery and how physical addresses, in this case Ethernet MAC addresses, are used for delivery within a network.
In this video, we're going to look at how we get information about the various network interface cards that are contained in our PCs. In the case of this laptop, I have both a wired and a wireless NIC. In order to view the properties of these devices, I need to go to the Network and Sharing Center. I can do this easily by going to the System Tray icon, right-clicking, and opening the Network and Sharing Center. This brings up the list of connections that I currently have active. As you can see, this is my computer, and I have multiple networks that are connecting to the internet. To look at the individual adapters, I need to go to the Change Adapter Settings. As you can see, I have a local area connection, which is a wired connection. You may be able to see the wire coming out of the back of my laptop. And I also have a wireless network connection. To view the properties of a particular connection, all you have to do is right-click and go down to the properties. There are a number of different properties that are associated with a network adapter on a Windows PC. Usually what we're most interested in are the settings for the Internet Protocol. In this case, we're going to view the properties for the IPv4. If we go in here, we can see that our device is receiving its IP address automatically. That means it's being given out by a DHCP server and was not configured statically. If I then go out to look at my wired network adapter, do the same exact thing and go to the properties and choose IPv4, you can see that on this adapter, my IP address was statically configured. That means an administrator assigned the IP address to my PC specifically, and it was typed in manually. More information can be gained by looking at the status information of this particular connection. I can see very briefly that I can get to the internet and that my device has a very good signal coming from the wireless access point. If I go into the details, I can even get more information. You can see here the different type of connection that I am going to, where I'm getting my DNS. And my DHCP configuration for this particular adapter will expire on Wednesday, December the 14th, and I'll have to renew it from the DHCP server. You can get the information about the MAC address, about the type of connection, and the wireless networks on which you're connected. In the local area connection, the information that you get is slightly different. It tells you right now that in the case of my wired network, I am not getting out beyond the first hop of my network, and that my connection itself is enabled and it is at 100 meg. Again, we have the details where I can get my MAC address, and I can also see my IPv4 address, and if I had an IPv6 address configured, it would also be displayed. Now, most of this information that you see in the NIC driver information status can be also viewed by going to the command prompt within Windows and doing an IP config. ipconfig has a number of options. The most commonly used one is the /all, which gives you much more information about how your device is configured. As you can see here, here is my adapters that I have for wireless and also for the wired connections. It is a very common practice that you have to find the MAC address, the IP address, and the current status of a PC adapter. So this is a skill you will get a lot of practice using. In this video, we're going to talk about the benefits of a hierarchical design when planning a network. Usually networks grow kind of organically. We start out with a small device and a few workstations. Think about your home network. You know, you have a couple of computers and you have some other devices, perhaps a printer, and perhaps maybe a game console. And all of these things plug in or connect wirelessly to your home network. But imagine that if you began a home-based business, all right? Your network would then need to grow. You might need some additional devices, some additional workstations. You might need some additional things like scanners and printers. So I might have a scanner out here and maybe another printer. And then all of a sudden I realized that my small little home networking device no longer has enough ports to support all of my various devices. As my small business grows and we remodel the garage to put it in, now I have to have another device. And usually we attach that device to the other device, and then the network begins to grow organically. This is true of your home network, but it's also true of enterprise networks. Many times businesses of all different sizes don't think about how they're creating their network. They just allow it to grow as they need more devices on the network. But pretty soon, we end up with a network that has mission-critical devices, say, for example, a server that your customers needed to get to, attached with things that really don't need to see that types of traffic or might actually even interfere with it in the case of the game console or someone, downloading a movie. So basically, a network that just grows organically is sometimes not all that efficient. So what we see is, over time, a different type of network architecture has become pretty much the standard, and that is called a hierarchical network design. In a hierarchical design, we think about how are we going to organize our network such that we have important things like servers separated from the user groups that might be, again, those people downloading Netflix or playing a video game. And we want them separated from the users that have to be critically important. Now, you also will see in enterprises and small businesses, this process is repeated multiple times. And hierarchical networks are able to scale because they are logically designed in a manner such that traffic that needs to go from these people to these servers does not need to travel over to the areas of the network where it's not necessary. Now, we had a little discussion earlier about broadcasting. Broadcast packets go to everyone that is in the same local network, meaning the same area of the network that is only connected by a switch. So in this instance, all of the broadcast traffic that is generated by the various devices, and even though I've only drawn a couple, in some cases this could be hundreds of devices. So all of the traffic that's generated by these devices will remain in this area of the network. So hierarchical networks scale quite well. Now, when the hierarchical network needs to connect to other networks, we will have other devices that provide the connectivity to get out to, say, the internet. In a hierarchical network design, there are names given to these various layers. Devices that actually connect to users and other end user devices reside at the access layer. The primary function of the access layer of the network is to provide an entrance point for devices to get on the network. Some types of things that are at the access layer are end user computers, but you'll also see IP phones and access points that provide wireless entry. And at some degree, you will see servers and services being provided at the access layer. The next layer up is the distribution layer. The distribution layer layer's main function is to interconnect the access layer networks and to direct the traffic such that traffic that needs to stay local stays local, and traffic that needs to traverse to remote networks actually has a path to use to get from one network to the other. Now, above all of that is the core layer. The core layer is responsible for the high-speed processing. So in this case, we have all of our users that need to get to the internet. So our core layer is going to take care of aggregating all of the traffic that's coming from these various devices and making sure that it efficiently is transmitted across the WAN links to the internet. So basically, this is one of the main reasons why we need to think about the planning part of our networks before we're building them. It's not really critically important when you're building a home network, But once you start into a network that needs to be up and operational most of the time, you really have to think about having a design that a failure of this component does not impact all the rest of the network.
In this video, we're going to take a look at how Ethernet switches work. Ethernet switches operate at the layer 2 data link layer of the OSI model. That's because they make their forwarding decisions based on the layer 2 information, the Ethernet header information of the Ethernet frame. Ethernet switches have MAC address tables. In this example, the MAC address table is already fully populated. We'll learn in a later video how the MAC address table gets built. But let's see how a switch uses this information. Here we have 4 hosts, H1 through H4. I have on each host an abbreviated MAC address, like AAAA for host 1. That's the MAC address of its Ethernet NIC. So if we have H1 going to send an Ethernet frame to H4, well, it builds an Ethernet frame with the source MAC address of its own MAC address. So in the source MAC address, we'll put AAAA, the MAC address of H1, and the destination MAC address will be that of H4, DD, DD. Once again, these are just abbreviated MAC addresses. So this Ethernet frame gets forwarded by H1 and is received on the switch on its Ethernet port, Fast Ethernet 01. The switch, we're going to learn later how it builds this table, but to forward the information, it looks at the destination MAC address of the Ethernet frame. The destination MAC address is DDDD. So it looks in its MAC address table for that MAC address, and here it is, DDDD, which is on port FA, Fast Ethernet 04. So the switch will forward this frame only out Fast Ethernet 04 towards the destination. In this video, we're going to take a look at how a switch builds its MAC address table. Once again, a switch makes its forwarding decision based on layer 2 information. In this case, the Ethernet header information of the Ethernet frame. So let's take a look at how this switch builds its MAC address table. On these 4 hosts, I have abbreviated MAC addresses, AAAA through DDDD. So here we're going to have H1 send an Ethernet frame to H4. So the source MAC address will be AAAA, the MAC address of H1's Ethernet NIC, and the destination MAC address will be that of H4's Ethernet NIC, DDDD. Okay, so H1 sends that frame onto the Ethernet switch. When the switch receives any Ethernet frame, the first thing it does is it looks at the source MAC address and says, have I learned anything? And what it's looking at is it sees that on its port, Fast Ethernet 01, is the source MAC address AAAA. Does that exist in its table? And it sees, it says, no, it doesn't. Because it doesn't already exist, it adds this source MAC address to the incoming port, Fast Ethernet 01. So let's put that right there. So that's how the switch builds its table. Now it wants to go ahead and forward the frame. So now it looks at the destination MAC address. It says, is this MAC address in my table? And as we can see, DDDD is not in its table. This is known as an unknown unicast. From the perspective of the switch, it's like, I don't know where to send it. So what it does is it acts like the old Ethernet hubs. it will actually send it out every port except the incoming port. So each one of these devices will actually receive this Ethernet frame. When H2 receives it, its Ethernet NIC card compares its MAC address to the destination MAC address of the Ethernet frame and goes, we're not a match. So it ignores the rest of the frame. See, H3 does the same thing. My MAC address doesn't match the MAC address of the destination MAC. Ignore the frame. H4, when it receives this Ethernet frame, its Ethernet NIC card goes, yeah, that is my MAC address. We are a match. So it goes ahead and receives the entire frame. Now let's see what happens when DD sends an Ethernet frame back to AAAA, or H4 sends an Ethernet frame to H1. Okay, so in this case, we have H4 as the source, and the destination is H1. Now, so far, this is the MAC address table of our switch. So H4 sends the Ethernet frame. It's received on port fast Ethernet 04 by the switch. Remember, the first thing a switch does, it wants to learn. It examines the source MAC address and says, have I learned anything new? It says, I've received this source MAC address on my port fast Ethernet 04. It's not in my MAC address table. So it adds the MAC address. Next, it says, I need to forward the frame. Do I know where the destination MAC address is? And it looks it up and says, yeah, I know that's on my fast Ethernet 01 port. So it goes ahead. In this case, it knows about where this destination MAC address is, and it can filter the frame and just send it out this single port. So you can see how Ethernet switches build their tables, learn about where the Ethernet source MAC addresses are, and then can start to forward these frames out specific ports. Let's take a final look here at another frame going from H1 to H4 and see how things have changed now. If H1 has another frame to send back to H4, the source MAC address is AA, the destination MAC address is DD, DD. And let's take a look at the difference from the first time this happened. The frame enters the switch. The switch says, do I know about this source MAC address on fast Ethernet 01? It says, yeah, I've learned about it previously. Okay. So switches tend to keep this information in there for about 5 minutes. It says, okay, I've learned that, no problem. How about forwarding the frame? Where am I going to send it? So it looks at the destination MAC address, says, do I know where DDDD is? It says, this time I do know. It's over here on port fast Ethernet 04. So instead of sending it out all ports like we did originally when this information was not here, now it can send it out just fast Ethernet 04 on its way to H4. In this video, we're going to take a look at an Ethernet broadcast. An Ethernet broadcast is when the destination MAC address is 48 1-bits, or in hexadecimal, all Fs. So looking at the animation here, we have H1 going to send a broadcast to all the other devices. This might be a message that it needs all the devices in its network to receive. So we can see H1 sends the broadcast. When a switch receives an Ethernet broadcast, it floods or forwards the Ethernet frame out all ports except the incoming port. The result is all the devices in the network will receive the broadcast. If we have a router in the network, it will receive the broadcast also. However, the router will not forward the broadcast on to other networks. In this video, we're going to introduce ARP, Address Resolution Protocol. ARP is used when we know the IPv4 address where we want to send the packet, but what we don't know is the device's Ethernet MAC address. For example, here we have PC1 that wants to send a packet to the destination IPv4 address of 192.168.1.9, the FTP server. PC1 knows the IPv4 address of the FTP server, but what it needs to know is its MAC address, because it needs to encapsulate this IPv4 packet in an Ethernet frame. So what PC1 does is it first looks in its ARP table. It looks for the IPv4 address of 192.168.1.9. If the address is not in its ARP table, it will send out an ARP request. So the animation shows PC1 sending out the ARP request. Notice that the ARP request is an Ethernet broadcast. What that means is when the switch receives this Ethernet broadcast, that's a destination MAC address of all 1-bits, the switch will flood the Ethernet broadcast, the ARP request out all ports except the incoming port. The reason for the broadcast is PC1 needs to know who on this network has the IPv4 address 192.168.1.9. It's saying, hey, everybody on my network, whoever has 192.168.1.9 as your IPv4 address, please reply back to me with your MAC address. So this ARP request goes out to every device on the network, including the router. Now, when the router receives this Ethernet broadcast, it will not forward it out other networks. So the Ethernet broadcast, this ARP request, stays on this network. So as we can see, the ARP request goes to everyone, and the FTP server says, hey, that's my IPv4 address you're looking for. I'm going to send you back a ARP reply with my MAC address. Now PC1 has the Ethernet MAC address of the FTP server at 192.168.1.9 and can now send that packet in an Ethernet frame to the FTP server.
In this lesson, we're going to talk about how, as networks grow, it becomes necessary to begin to divide them from a single large local network to multiple smaller local network segments. Let's look at our enterprise here that we had drawn on the board. And this enterprise consists of three major departments. We have network management, we have the accounting department, and we have the sales department. Now, some of the reasons that you might divide a network into smaller components, the first one is just to limit the amount of broadcast traffic that goes across the network. Anytime you generate a broadcast, even though I'm way over here in network management, my computer and all of the other devices on the network will be forced to accept that broadcast and process it. Most broadcasts don't contain information that every single device needs to know. So there are a lot of broadcasts that are being processed by your device that are eventually being thrown away because the information contained in that broadcast really isn't needed by any application on your device. Now, that's one reason that we might want to divide a network, is to contain broadcasts, to make smaller broadcast domains. And the term broadcast domain refers to the area that hears a broadcast. So in the case of this network, because all of the devices are connected by switches, all the broadcasts would be heard by all of the connected devices. Now, another reason that we might want to divide our network is for security purposes. We may not want people in the sales department to be able to see the devices and servers or use the printers that are located in the accounting department. We might also not want the accounting department to be able to access the network control mechanisms that are in the network management department. So that's another reason why we might want to divide our network into smaller pieces. A major reason that we might want to divide the network is, say, for example, our accounting department is moving. They've got a new building or a new office on a different floor, and they're going to be moving outside of where our local network can actually service them. So taking and dividing something by geographical location requires us to make our network segments much smaller. So basically, how do we do that? How do we divide a network that is one large network into smaller pieces? One of the ways we do is with a router. In all networks, the local network, meaning the network that belongs to the business or the home or the enterprise, that network is separated from the internet by a router. When you buy your home network connection, your service provider puts a router at your home. That is so that the traffic that is generated by your network does not end up at the internet. The internet would not be happy with that. So basically, when we add a router, the router enables us to divide the network and also to divide the broadcast domains. So if I were to insert routers into this network diagram, let me draw some routers here. When I insert routers into this diagram, I have now taken one relatively large network and divided it to three separate networks. On a router, every interface on a router connects to and defines a separate network. And when I'm talking about separate networks, we're talking about both broadcast domains, but also different IP networks. Different networks that have different sets of IP addresses that identify all of the people within the network as being on the same IP network. So basically, to recap, the reasons that we divide a network: we divide the network because of security. We divide the network because we want to maintain smaller broadcast domains. And we divide the network because we may be moving things to different locations. where a single large network can't reach.
In this video, we're going to take a look at how a router forwards packets from one network to another network. So in this example, we have host at 10.0.0.1 wants to send a packet to 192.168.1.2, which is in another network. So the source IP address of the packet will be 10.0.0.1. The destination IPv4 address of the packet will be 192.168.1.2. So H1 sends the packet to its default gateway, the router. Now it sends it to the router because H1 knows that the destination, H4, its IPv4 address is on a different network. The router receives the packet and it looks up the destination IPv4 address of the packet in its routing table. It notices that the IPv4 address, the destination IPv4 address, 192.168.1.2 is on the 192.168.1.0 network. And that network is on its Fast Ethernet 02 interface. So the router will go ahead and forward this packet out its Fast Ethernet 02 interface towards the final destination. Now in this case, H1 has a packet to send to the destination IPv4 address 255.255.255.255. If you remember, that's a broadcast address. So a broadcast will be sent to all devices on its network. You'll notice the router will receive this broadcast, but will not forward this packet out to other networks. In this video, we're going to take a look at how messages travel within a network and also between networks. So in this first part, we have host H1 at 192.168.1.10 going to send a packet to the IPv4 address of H2, 192.168.1.20. H1, the source of the packet, builds the IPv4 packet with its own address as the source, 192.168.1.10, and the destination IPv4 address of 192.168.1.20. Now, the first thing H1 needs to determine is, are we on the same network? And it notices that its own network address is 192.168.1.0. That's the network it belongs to. And it actually uses its subnet mask to do that. Then it looks at the destination IPv4 address, using its own subnet mask, H1, determines that H2 at 192.168.1.20, they're on the same network. They both begin with 192.168.1. So we're on the same network. What that means to H1 is that it can send this packet directly to H2. It does not have to send it through its default gateway, the router. It can send it directly. So H1 is going to build the Ethernet frame with its own MAC address of its Ethernet NIC, AAAA, as the Ethernet source MAC address. The destination MAC address is, okay, I can send it directly to H2 because we're on the same network. So it says, I just need to know the MAC address associated with the destination, 192.168.1.20. In that case, H1 checks its ARP table. And we're going to assume that it has that information in its ARP table. It knows that 192.168.1.20 has the MAC address BBBB. If it doesn't know that, remember it sends an ARP request, gets an ARP reply, adds it to the table. Okay, so now H1 can go ahead and send this Ethernet frame towards the switch, and it gets sent directly to H2. In this next part, we're going to have H1 at 192.168.1.10, that's its IPv4 address, send a packet, an IPv4 packet, to 192.168.2.50, host H3. So H1, the source of the packet, builds the IPv4 packet. The source IPv4 address is its own IPv4 address, 192.168.1.10. The destination IPv4 address is the final destination, that of H3, at 192.168.2.50. Now H1 needs to determine, is the destination IPv4 address, that of H3, on the same network as myself? Now, once again, it knows that its IPv4 address, 192.168.1.10, that it's on the 192.168.1.0 network. It looks at the destination IPv4 address using its own subnet mask. It determines that the destination address is on a different network. It is not on the 192.168.1.0 network. It's on 192.168.2.0 perhaps. All it knows is it's not on my network. So H1 says, okay, I cannot send this packet directly to the device. I need to send it to my default gateway, the router. So H1 knows the IPv4 address of the default gateway of the router. As part of the configuration information every device must have to reach other networks. So it knows the IPv4 address of the router is 192.168.1.1. What it needs to know is, what is the default gateway? What is this IPv4 address's MAC address? So it checks its ARP cache for that MAC address. We're going to assume that it already has that information in its ARP cache. The Ethernet NIC associated with this interface, with this router's interface, we're going to abbreviate it at 1111. And again, if it didn't know that information, it would send out an ARP request, get an ARP reply from the router. Okay, so now this Ethernet frame gets sent from H1 and is received by the router. The router receives this, says, yes, that's my destination MAC address. This frame is for me. So what it does is it actually removes this Ethernet header information. Now the router is going to do its job at what we call layer 3 forwarding. It's going to do routing. it looks up the destination IPv4 address of the packet. It looks that up in its routing table. It says, okay, this destination IPv4 address, 192.168.2.50, oh, that's a member of the 192.168.2.0 network in my routing table. I can reach that network by sending the packet out Fast Ethernet 02. So it wants to send this packet out this interface. So it's going to encapsulate it now in a new Ethernet frame. So the new Ethernet frame will actually have the source MAC address of this router's network interface card. So it's actually going to have the source MAC address of 2222. Remember, Ethernet layer 2 is for network interface card to network interface card communications in the same network. Okay, we're almost there. The next thing it has to do is says, okay, oh, the destination IPv4 address, that's on my network. I, router R1, can reach that device directly. I need to know the MAC address associated with this IPv4 address. So guess what? It actually checks its own ARP cache for that information. And we're going to assume that it has that information, that it knows that 192.168.2.50, this device right here, has the MAC address CCCC. Again, that's abbreviated, but let's go ahead and use that. CCCC. So now it can send this Ethernet frame out the Fast Ethernet 02 port. The switch forwards that on to H3. It says, yes, the destination MAC address that is associated with the MAC address of my NIC card. This Ethernet frame is for me. It receives the packet. It says, yes, that IPv4 address is my IPv4 address, receives the packet. And that's how a packet is sent from H1 to H3 across different networks.
In this video, we are going to discuss how computers send messages when the source and destination are not on the same network. In this case, we are going to have PC0, which if we look at its IP addressing structure, shows that it is on the 192.168.1 network, whereas PC2 over here is on the 192.168.2 network. So because they're not on the same network, communications from one PC to the other PC have to travel through a router. If PC0 and PC1 were talking to each other, they would be using the ARP protocol. They would send an ARP message, and then they would respond with the MAC address. And the frame would be addressed from the MAC address on PC0 to the MAC address on PC1. But PC2 is on another network. And as you learned earlier, broadcasts do not travel through routers. So when PC0 would send an ARP for PC2, that ARP, being a broadcast packet, would not go through the router. So in this case, PC0, if we look at its IP configuration, it has a default gateway configured. Now, what is the purpose of a default gateway? A default gateway is the IP address of the router interface attached to the local area network segment where PC0 is located. So if we go back and we look at router 0, we will see that router 0's IP address for the interface 192.168.1.1 for the interface that's attached to the LAN that PC0 is connected to. We can also see that the router has an interface configured for the other network as well, 192.168.2. Routers keep tables of the networks on which they're connected and also other networks that they are told about, either by an administrator or information that they receive from other routers in the network. In this case, we only have the two networks connected. So if I do a show IP route command to view the routing table on this router, it will show two connected networks, the 192.168.1 network and the 192.168.2 network. So let's look at what happens when we send a ping packet from PC0 to PC2. I'm going to open up the simulation mode of Packet Tracer so that you can actually see the packets go back and forth. Let's send a packet from PC1 to PC0. So the first thing I want to find out is what is my IP address. So I'm going to use the IP config command to find out what my IP address is. Then I'm going to ping PC0. As you can see, the packet's being sent, and you'll notice up here that I'm sending an ARP request. That ARP request is going to go up to the switch, and then because it is a broadcast message, it's going to go to all of the devices attached. PC0 is going to respond back to me with its MAC address so that I can send the communications directly from PC1 to PC0. And you can see that the packet is going directly. Now, PC2 is on a different network. So if I want to ping PC2, let's take a quick look at PC2's IP address. I'm going to use the IP config command again. And we can see that PC2 is on the 192.168.2 network. So I'm going to go ahead and go back to my PC1. And it's still in the process of pinging, so let's go back to real time. I'm going to go back into simulation mode so we can ping PC2. This time I'm going to ping PC2 to 168.2.10. And now we can see that our packet is going to go to the default gateway. We're going to be ARPing for the address of the default gateway instead of the address of PC2. When the default gateway responds, the ping packet will then be sent to the router. When it gets to the router will send the packet to the correct network. It will look in its routing table, which we saw earlier. As you can see, the process to communicate with a device that's on your own network is different from the process to communicate with a device that's located on a different network. Anytime you go from one IP network to another IP network, you need to use the services of the router. And a router determines how to get to the other networks by looking up the items in its routing table.
In this video, we're going to take a look at the binary number system. We're also going to see how to convert from binary to decimal. First, a brief look at the fundamentals of number systems. In all number systems, the first digit begins with 0. So whatever base we're working in, that tells us how many digits or how many numbers are in that number system. For example, decimal, base 10 number system has 10 digits. Starting at 0 through 9, that's our 10 digits. Binary is base 2. Base 2 has 2 digits. Starting at 0, 0 and 1 are our 2 digits. So the first column in our number system is always the column of ones. Whatever base we're working in, the next column is that times the previous column. Let's take a look. In base 10, the first column is the column of ones, our rightmost column. Base 10, the next column would be 10 times 1, or 10. The next column would be 10 times that, 10 times 10, or 100. The next column, 10 times 100, 1,000, and so on. In base 2, we also start with the column of ones. Base 2, the next column would be 2 times the previous column, or 2. The next column after that would be 2 times 2, 4. The next column, 2 times 4, 8, and so on. So in base 10, we said the first column is the column of ones. Next column is 10 times that, 10, then 10 times that, 100, etc. What digits can go in each of those columns? Well, any digits in our number system, 0 through 9. So whatever I put in the ones column is how many ones I have. Like 1 is 1, 1. 2 would be 2 ones. 3 would be 3 ones. 9 would be 9 ones. And that's actually the last digit in our number system. So 10 would be 1 in the tens column and 0 in the ones column. That gives us our 10. So the 1 in the tens column means the number of tens as opposed to the 1 in the ones column, which is the number of ones. 99 would be 9 tens and 9 ones. 100 would be 1 100s, 0 tens, and 0 ones. Now this may seem really basic, but understanding base 10, the decimal number system, you can understand any number system. Let's take a look at the binary number system. The binary system, the first column is our column of ones. The next column, because base 2 is 2 times this column, so that would be 2. The next column, base 2, 2 times 2 is 4. The next column would be 8, and we'd keep going, but we're going to leave it at this. Okay, so what can go in each one of these columns? Well, we're using base 2 binary. So we only have a choice of 2 digits, a 0 or a 1. Let's take a look. So a 0 in binary, 0 ones, that's equivalent to a 0 in decimal. A 1 in the ones place is equivalent to 1 in decimal, a 1. Now remember, in binary, we can only use a 0 or 1. So 1, 0, what this means is how many 2s do I have? I have 1, 2, and 0 ones. That equates to 2. 1, 1 in binary is 1, 2, plus 1, 1. 2 plus 1 is 3. 1, 0, 0 in binary is 1 4s, 0 2s, 0 1s. So we have 4. Wherever we have a 1, we just add up that column. If we have a 0, we don't add that column. It's that simple. So as we can see, 5 would just be 1 0 1. 6 would be 1 1 0, 1 4, 1 2, 0 1s. 7, 8 would be 1 in the 8s and 0 in the 4s, 2s, and 1s. 9, 10. 10 would be 1/8 plus 1/2. 8 plus 2 is 10. 11, 12, 13. So 13 is 1/8 plus 1/4 is 12 plus 1 is 13. 14, 15. 15 is 1/8 plus 1/4 plus 1/2 plus 1/1. 8 plus 4 plus 2 plus 1 is 15. So what would 16 be? You're right. 16 would be, we'd have another column over here of 16s. 2 times 8 is 16, so we'd have another column over here, and it would be 1 in the 16s column, followed by 0, 0, 0, 0. So let's look at how to convert from binary to decimal. It's very simple. So given this binary number, what would be the decimal equivalent? You're right. All we have to do is add up. Wherever we have a 1, add up that column. We have 1, 2, 0, 1s. That gives us 2. What would this be? You're right. 1/8 plus 1/2, that's 10. How about this? We have 1 in the 16s, 1 in the 1s. What's that give us? You're right. 16 plus 1, 17. How about this? Notice that each column is 2 times the previous column. So 164 plus 1/4, see that's 68, plus 1 in the 2s, that's 70. I have 0 everywhere else. 70 is the answer. How about this one? Oh, 1 in the 128s. What else do I have? 1 in the 2s. 128 plus 2, that gives us 130. And let's take a look at this last one here. Oh, that looks tough. A lot of adding to do, isn't it? So we'd have to add 128 plus 64 plus 32 plus 16 plus 8 plus 4 plus 2 plus 1. What does that give us? 255. And there's actually an easy way to figure that out when we have all 1s in this column. What would be the next value after 128? The next column? Well, that would be 256. So 256 would be 1 in the 256 column, and then all zeros. So if the next column is 256, and we have all 1s here, we just subtract 1 from 256, and that's 255. That doesn't make sense. Don't worry about it. All you have to do, again, is add up wherever we have a 1 in that column. Add those column headings up, and we get the answer.
In this lesson, we're going to talk about how IP addressing works in a multi-network environment. Originally, when we talked about IP addressing, all of the devices that we were communicating with were on the same local network. So how does IP know when a device is on a different network? So basically, let's look at our divided network here. We have the network management department, the accounting department, and the sales department. Each of those departments have an IP addressing structure that is unique to their local area network. Now, how do we know what part of the IP address differentiates between the networks? Basically, every IP address has a structure to it, and that structure includes a network component, and let's just take a network address that's up here. It has a network component, and it has a host component. All of the devices in the sales department local network will have to have the same first 3 octets of their IP address, because this network is represented by the 192.168.3. The individual host numbers, which are the last octet, will have to be unique. In other words, your computer here has the address of 192.168.3.10. No other device on that same network can have that same IP address, because every host part has to be unique. So in a local network, the network portion has to be the same, and the host portion has to be unique. Now, if we move over to the next network over here, we can see that the network portion is different. We had the 192.168.3 network over here. We have the 192.168.2 network over here. If I come over to network management, where I'm located, you'll see that I'm on the 192.168.1 network. It's very important to remember that if your IP address is such that your network portion does not match what your local area network is assigned, you will not be able to communicate. So if I accidentally grabbed a computer from over here and moved it over here, and I did not change the IP address, it would not be able to communicate over the IP network. So basically, in order to have an IP network, the network portion of the address must be the same for all of the computers on the local area network. In this lesson, we're going to talk about how does an individual host computer know whether or not the destination it's trying to reach is on its own same network. When you're communicating on your same network, there are different rules than when you are communicating to a remote network. When you communicate on your own local network, the device sends an ARP in order to retrieve back the MAC address of the destination device. Then it creates its frame with the destination MAC and its own MAC as the source MAC and sends it on its way. Whenever you have to communicate with a device that's not on your same local network, you can't just ARP for it, because an ARP is a broadcast communications, and ARPs do not traverse outside of the same local network. So for example, if I was communicating from this host and I wanted to communicate to another host on the same network, I would just ARP for their MAC address, and then I would receive back the response. Now, Because this network is divided and we have a router in between, if this host is attempting to talk to a host over here, it would have to send the packet to the router in order for it to be forwarded. But how does the individual device know whether or not to ARP? One of the ways that IP is designed is that every IP device has to have both an IP address and a subnet mask. The subnet mask tells the device how many bits of its IP address belong to the network portion and how many bits belong to the host portion. As we talked about earlier, every IP address has a component of network and host. In this case, this subnet mask tells us that the first 3 octets are all set to 1, which means the first 24 bits of the address represents the network portion. So basically, if, for example, this host is trying to send a packet over to the server in the accounting department, the very first thing it would do is it would take the destination address. And the destination address is 192.168.2.50. It would take this address and it would apply its own subnet mask. And I know that seems a little odd. Why wouldn't it try to find out the subnet mask of this destination? Well, it doesn't need that subnet mask because what it needs to find out is the network portion of this address exactly the same as the one that was assigned to the particular host. So the IP address represents ones in these areas. So we have 8 ones, 8 ones, and 8 ones. This makes this a /24. So what the host actually does is it converts this destination IP address to the corresponding binary, 1s and 0s. Then it takes the first 24 bits and it determines whether or not the first 24 bits of this address are identical to the first 24 bits of this address. And we'll talk in just a minute about how that binary process works. But in this case, assuming the first 24 bits do not match, okay, the host then says, okay, they're on the 192.168.2 network, and I'm on the 192.168.3 network. So basically, the host has determined I can't just ARP for the MAC address for this host. I'm going to have to actually send this to my router and then have the router forward it on. So how is it that the computer, which only functions in binary, actually determines whether or not a destination address is on the same network? The computer uses a process called binary ANDing. Okay, binary ANDing, despite its name, is more like binary multiplication. Basically what happens is if host 192.168.3.10 wants to send a packet to the destination 192.168.2.50, it first has to figure out, is that address on my same network? So it takes that address, and as you can see here, I've written the binary representation of that address on the board. Now, in binary, we don't actually have the decimal. I only put it there for illustration purposes so that you could see where the octets were broken. Now, what happens is it takes the subnet mask and converts, well, it doesn't convert it to binary because it's already binary in the computer, but it takes the binary subnet mask and it takes that subnet mask and ANDs it with the actual IP address of the destination device. So in binary ANDing, it is essentially 1 times 1 rather than 1 plus 1, which you would think from the term ANDing. But in binary ANDing, this would be the representation. So I would have 1, 1, 0, 0, 0, 0, 0, and 1, 0, 1, 0, 1, 0, 0, 0. And then I would have 0, 0, 0, 0, 0, 1, 0. And lastly, I would have 0, because if you multiply any of these by 0, the result is going to be 0. So basically, what I have identified in the computer is the bits that make up the network portion of the address. Now, if we were to convert these back to the decimal, which computers do only really when they want to show something to us humans, we would convert it back to 192.168.2.0. This is the actual network address of the destination. Comparing that to the network destination of the source host, we can see that they are not on the same network.
All devices on an IPv4 network need a 32-bit logical address in order to communicate. This 32-bit logical IPv4 host address consists of a network portion or network ID on the left and a host portion or host ID on the right. The length of these depends on the size of the network. Larger networks will have a longer host portion. A network can be thought of as a range of addresses. All devices on the same network have the same bit pattern for their network ID, but they will have a different host ID. Some addresses in this range are reserved and have a special name and meaning. For example, the first address in the range is used to identify the network itself and cannot be assigned to any host. It is referred to as the network address. The last in the range is called the broadcast address and is used to send a message to all devices on the network at once. It also cannot be assigned to any host. All the IP addresses between the network and the broadcast addresses make up the usable or valid host range and can be used to address the hosts on the network. Let's take a look at how these addresses are determined. In order to forward data, a device needs to know what network it's on. Using their host IP address, their subnet mask, and a process called binary ANDing, a device can find what's referred to as the network address. This address represents the network to which the host belongs and will be slightly different than its host IP. To do this, the device compares their host IP and their subnet mask bit for bit. If the bit values are both a binary 1, the result is a binary 1. If one or both of the bit values is 0, the result is a binary 0. Let's take a look at an example. Let's say we have a PC with a host IP address and a subnet mask of 192.168.2.38/24, and we'll use ANDing to find the network address of the host. Here's the host IP in binary. Here's the subnet mask in binary. If we compare them bit for bit, we can see that a 1 and a 1 results in a 1 and a 1 results in a 1, a 0 and a 1 results in a 0 and a 1 results in a 0, and so on until we have compared all 32 bits. Notice that the last octet is all binary zeros. Because we are using a /24 subnet mask, the first 3 octets represent the network portion, and the last octet is the host portion. Network addresses will always have binary zeros in their entire host portion, however long it is. In this case, the last 8 bits. If we convert to dotted decimal, we can see that this host belongs to the network 192.168.2.0/24. Now let's determine the broadcast address for this network, which is used to send a message to all devices on the network at once. Whereas the network address had all binary zeros in the host portion, the broadcast address will have all binary ones. Since the host portion in this example is just the last octet, to determine the broadcast address, we keep the network portion the same and change the host portion to all binary ones. This results in a broadcast address of 192.168.2.255. Next, we'll determine the usable host addresses, which lie between the network and the broadcast addresses. The first usable host in binary will be all binary zeros with a binary 1 at the end of the host portion. Converting to dotted decimal, this tells us the first usable host on this network is 192.168.2.1. Lastly, we'll determine the last usable host, which will be all binary 1s with a 0 at the end, the opposite bit pattern of the first usable host. Converting to dotted decimal, we get 192.168.2.254. Let's recap our calculations. We began with the host IP address of 192.168.2.38/24. Using binary ANDing, we determined that this host belongs to the network 192.168.2.0. Keeping the network portion the same, but placing all binary ones in the host portion, we determined that the broadcast address for this network is 192.168.2.255. Again, keeping the network portion the same, but changing the host portion, we determined that the usable host range for assigning addresses to devices on this network is 192.168.2.1, which is one number up from the network address, and 192.168.2.254, which is one number down from the broadcast address. You can see that our original host IP address falls within this range. Things to keep in mind when working with IPv4 addresses. All IPv4 host addresses are 32 bits in length. A portion of the address represents the network that the host belongs to, and that starts at the left. The remaining part is the host portion, which identifies the host on the network. And there are two special reserved addresses on every network that can't be assigned to hosts. One is the network address, which is the lowest in the range of addresses and represents the network that all the devices belong to. And the other is the broadcast address, which is the highest address in the range and can be used for a shout out to all devices on the network at once. Thankfully, there are shortcuts you can take for calculating these addresses without having to convert to binary first. But examining these addresses at the bit level should help you understand how network devices interpret them and also how the dotted decimal format is derived.
First of all, when we're talking about classful IP addressing in networks, we're talking about Class C, Class B, and Class A addresses. Now, what makes a Class C, Class B, and Class A address and network? Two things: the IP address and the subnet mask. In order to have a Class C IP address or Class C network, you need the IP address first octet to be a number between 192 and 223. You also need the subnet mask to be 255.255.255.0. As long as you have these two requirements, you would have a Class C IP address and Class C network. To have a Class B IP address and network, you'd need the IP address, the number in the first octet, to be a number between 128 and 191, and the subnet mask would need to be 255.255.0.0. For a Class A IP address and network, the first octet address number would need to be a number between 0 and 127, and the subnet mask 255.0.0.0. Now you might ask yourself, why these specific numbers, 0 to 127 for Class A, 128 to 191 for Class B, and 192 to 223 for Class C? It all has to do with the fact that the router and the computers see the IP addresses and the subnet masks in binary, not in dotted decimal notation. This is just the decimal representation of what the computer sees in binary. So if we look at it in binary and we take a look and convert the first octet in the IP address to binary, we see that in order to have a number between 192 and 223, the first 3 digits in binary, counting from left to right, need to be 1, 1, and 0. If the first 3 digits are 1, 1, 0, the number has to be between 192 and 223. And for Class B, if the number starts with a 1, 0, then the resulting number will be constrained to 128 to 191. And in Class A, as long as in binary the number begins with a 0, the number in decimal representation can only be 0 to 127. So the restrictions on the numbers 0 to 127, 128 to 191, and 192 to 223 are due to how the address functions in binary.
In this video, we're going to take a look at unicast IP transmission. So here we have host 172.16.4.1. It's going to send a unicast packet. That's a packet where the destination IP address is destined for a single device. And it's going to send it to the destination IP address of the printer at 172.16.4.253. So the source IP address is 172.16.4.1, and the destination IP address of the packet is 172.16.4.253. So we can see here that the packet goes from a single device to a single device, in this case the printer. And by the way, a source IP address can only be a unicast. What we mean by that is a packet can only originate from a single device. In this case, the destination address is also a unicast, meaning it's destined only for a single device. In this video, we're going to take a look at broadcast transmission. So we have a packet with the source IPv4 address 172.16.4.1 and a destination IPv4 address of 255.255.255.255. That's a special address, meaning it's destined for all devices on the network. It's known as a broadcast. So if we take a look here, the packet leaves the source 172.16.4.1, and notice that our Ethernet switch flooded out the packet out all ports except the incoming port, and it was received by every device on the network. Now, when this router receives the broadcast, it will not forward the broadcast packet to other networks. But a broadcast means every device on the network will receive the IPv4 packet. Multicast transmission is used to send a packet from a single device to a selected group of devices. IPv4 multicast addresses have a range from 224.0.0.0 to 239.255.255.255. So in this animation here, we're going to have a multicast transmission going from 172.16.4.1 to two selected hosts that are a member of the multicast group. But the only two devices that this packet is for 172.16.4.3 and 172.16.4.4. So we can see here that the packet leaves 172.16.4.1 and is received by multiple devices on the network. However, only 4.3 and 4.4 are the only two devices that are a member of this multicast group. So they're the only two devices that will actually process this packet.
Hi! In this lesson, we're going to talk about how DHCP works. Earlier, you learned that IP address assignments can be given out in two ways. Statically, meaning that someone actually sits down and configures the IP address, or dynamically, where the device gets its address from a DHCP server. DHCP means the protocol that is being used to obtain that IP address. DHCP stands for Dynamic Host Configuration Protocol. So how does that protocol work? The protocol describes a set of messages that go between the host wanting an IP address and the DHCP server that gives out the IP address. So basically, what we have is we have a host system that sends out a packet called a DHCP discover. And what this packet is doing is actually looking for a DHCP server. The packet is a broadcast packet, and it contains the MAC address of the device requesting the IP address, and it is destined for any device on the network that's configured to be a DHCP server. What kind of devices can be DHCP servers? Well, typically in a home network, the home router, the wireless router or the wired router, is configured to give out DHCP. In larger environments, often this is a server that would be doing other functions like Microsoft domain controlling, or it might be a Linux server that also doubles as a web server. So basically, the DHCP server can be a number of different types of devices. So when the DHCP discover goes out, since it is a broadcast, any DHCP server attached to the network will hear that. The DHCP server then responds with the DHCP offer. The DHCP offer packet contains an IP address that the host, the individual device, could use if it accepts it. When the host receives the DHCP offer packet from the DHCP server containing the IP address, and here's the IP address that was sent, and the subnet mask, as well as the default gateway address. Once the host receives that, it sends back a DHCP request packet that it will accept the offer. And it will request the IP address that the server had sent it, 192.168.1.15. The device will then take this information and enter it into its IP address settings. And at that time, once the server receives the DHCP request, the server will send back a DHCP acknowledgement that will indicate to the host that the server is placing this IP address into its table associated with the MAC address that was sent from the host. There are two ways to get an IP address on a device. One way is to manually configure it, or statically configure it, as it's called in Microsoft Windows. And the other way to do it is to get it automatically from a device that provides DHCP. In the little network here that we're showing in Packet Tracer, we have 3 PCs attached to a DHCP-enabled router. Basically what this is a very similar device to what you would have at home. If you look here on the device itself, you'll notice that this device has a switch port, an antenna for wireless, and an internet connection. This type of configuration is available on almost every home wireless router. So basically what we're going to do is we're going to go in and we're going to look at how DHCP is configured on this device. Most home devices, home networking devices, have a GUI interface to make it easy to set them up. In the case of this device, you can see that I have some settings that are basic router settings. In this, on this router, we are going to enable DHCP, and as you can see by default, it's normally enabled. And you can see that an IP address has been already assigned to the router interface that faces the LAN. When the automatic configuration is received by the PCs, they're going to see this address as their default gateway. Now, the way that DHCP is configured is a group of addresses are reserved on a particular network to be handed out to hosts one by one. If you look here at the settings, it will say that the DHCP range will start at 172.16.0.100. So if we save this configuration and then we go to our PCs and enable each PC to get their IP address via DHCP rather than via the static configuration. So we're going to go to the desktop here, and we're going to look at our IP configuration, and then we're going to change it from the static configuration to getting its IP address via DHCP. And you will notice that immediately the device sent out a request for a DHCP address and received one from the DHCP server. You'll notice from the information that since this is the first PC to be configured for DHCP, it got the first available address. When we look at the other PCs and look at their IP configurations, if we change them over to DHCP, they will also get addresses, but they will not be the same address. It will be the next number up. Since we have our IP addresses set, now we can go out and test our network connectivity. So if I'm on PC 0, I'm going to go ahead and ping one of the other PCs. We know that since I have the address 100, the other two devices have the addresses 101 and 102. So we're going to try pinging both of those computers. And as you can see, we can reach that 101 computer, which is PC1 on our diagram. And then we will attempt to to ping PC2. And you can see we can reach PC2 also. So the information that was on the router configuration for DHCP determined what IP addresses would be assigned to all of the PCs on the network.